This screencast is to present the formula for computing the beating frequencies, but I don't want it to be just a little memorization of a formula. It needs to make sense to you, so I prepared just a couple of pictures that I hope will reinforce what we mean by beating and then how we compute the beating frequency. I drew these graphs using Mathematica. Here's a graph of cosine of t and cosine 0.8t. So we're in a situation where we have two similar frequencies, frequency of 1 over 2 pi and 0.8 over 2 pi. And here are their graphs. One's in blue and one's in red. And down below I have graph of cosine of t minus cosine 0.8t, and this graph is cosine of t plus 0.8t. The one thing that's not great in how I'm giving this presentation, this time axis only goes to 30, this time axis goes to 120, or goes to 40 pi versus 10 pi. So we can't look vertically and see the correspondence, but you will see that if I'm in this region and I'm subtracting the two, they pretty much cancel each other out through here as well. In the beginning they cancel each other out, and so you'll notice that when we subtract the two of them, we begin with very small amplitudes. Okay. Whereas here I'm adding the two of them, and you see that they're both at 1, so when we add them we're at an amplitude of 2. And then as they both go to 0, eventually, when we start adding them and they're both negative, we go to minus 2. And so this phenomenon is just shifted, the difference between subtracting cosine of t and cosine 0.8t and adding them. Very similar shapes, just one is shifted. It is more pronounced over here where we're working with the cosine of t and cosine of 0.9t. Here is the graph of their difference, and you'll see that the amplitudes vary, and at a certain point when they're opposite of each other and we subtract them, we get large values. But when they're in sync with each other and we were to subtract them, we get 0 values or smaller values. Here we are adding cosine 1, cosine of t and cosine 0.9t. We see the same phenomenon, but it is shifted. Now I just want to focus on the case where we're working with the difference of cosine t and cosine 0.9t, because the beating is very pronounced here. As the two frequencies are closer to each other, it's more pronounced. And so I want to reinforce the fact that when I subtract them, this is the graph we saw in the previous slide, and I can represent that with this trigonometric identity, that the cosine of the difference of two cosine functions can be written as 2 times the sine of the difference between them, at minus bt divided by 2. I factor out a t, but that's the formula, times the sine of their sum, or their average of their sum, at plus bt divided by 2. And here you see with Mathematica I'm graphing that function, 2 sine, and it's 1 plus 0.9 divided by 2 and 1 minus 0.9 divided by 2. And you see that this graph, going up and down, modulated in amplitude, is the same as just cosine modulates and up and down. Okay, same picture. So this trig identity works. Or if we added the two functions, cosine t plus cosine 0.9t, here's the corresponding trigonometric identity. Same basic arguments, but now we're working with cosines instead of sines. And sure enough, with Mathematica, if I plot 2 cosine of t times 1 plus 0.9 divided by 2 and cosine of t 1 minus 0.9 divided by 2, we have identical graphs. Okay, so this graph, where it gets small, big, big, is the same as we have here. So here's a sum of cosines, and here it is represented as a product. In this form, as we look at this, the product of two functions, I can actually think of this whole first term as an amplitude. Clearly, a minus b divided by 2 is smaller than a plus b divided by 2. So of the two graphs, this graph has a smaller frequency, therefore a larger period. This is the graph that will be referred to as our beating amplitude, and it is this expression that we'll use to compute its frequency. So in both cases, if I were to graph this by itself, I would see that this has a much larger period than this graph. This argument is corresponding to these peaks. This is the period of the fast oscillation, and then the period of the slow oscillation goes from peak here to peak here. Okay, as I could draw it in, something like this. So this would be one period going from this point here to this point here. Okay, and so this is our slow. This is slow. This is fast. Okay, good. Finally, to reinforce what we're referring to as the beating function, I'm going to refer to something as beating envelope. Here, again, up above, I've used the product of the sine functions to represent our difference of cosines. And here I'm using the product of cosine functions to represent the sum of the cosines. And yes, they are just phase-shifted versions of each other. And in each case, I'm down below, I'm also graphing just the envelope. So I'm just graphing the positive function 2 sine a minus b over 2t, or in this case, 2 sine 1 minus 0.9 over 2t. That's this graph. And I'm also graphing its negative. So if you look in the Mathematica code, here you see I'm drawing 2 times sine of t 1 minus, and I had to cut off a little bit of it. And here's the negative of it, negative 2 sine t plus 1 minus 0.9 divided by 2. So that's this graph. Okay. So clearly, we do have a description of that envelope, and the period, we're seeing one full period here. On the next slide, I'll talk about our expression for that period. In the world of cosine, again, this is what our beating envelope looks like. Here's the top half, and then when I draw the negative of it, I get this. Finally, talking about the mathematical expressions for the fast and slow frequencies, I'm generalizing in our forced harmonic oscillator problems. We can potentially end up in one of two situations. We have a constant times cosine of one particular frequency minus a constant times cosine of a different frequency, b. The fact that these amplitudes are different will not affect the frequency of vibration. In the example as I did previously, I had the same amplitude in both cases, and probably it would have been a better illustration had I had them as different amplitudes. But it will not affect the fact that there will be beating, and that there will be a slow frequency and a fast frequency. When I look at an expression cosine of at, its period is 2 pi over a, but its frequency is a over 2 pi. And this one has a second frequency of b over 2 pi. On this side, if we were to be adding the cosine to another cosine, the same rules apply. There's no difference whatsoever in terms of computing the fast and slow frequency. We have two different frequencies. The slow frequency will always be the difference of the two divided by 2. And so in this case, our beating frequency will be a minus b over 4 pi. Our fast frequency, rapid response frequency, as it's called in the book, will be the sum, and I have a small mistake there. Let me just see if I can erase that before. I can't. So this should be a 4, of course. 4 pi. Okay, that's it. Thank you.